My name is Meredith Hughes. I'm visiting from Wesleyan University in Connecticut, and I guess it's my job to inject a little bit of reality into the end of the morning, now that you guys have been...
Highly overrated.
No. I love theorists. Some of my best collaborators are theorists. Okay, so with no further ado, I will actually tell you what I'm going to talk about today, which is, it's my job to talk about protoplanetary disks. And so I was supposed to talk about observations of protoplanetary disks here, and I figured I'd divide it in half along the somewhat artificial division of today I'm going to talk about dust in protoplanetary disks, and tomorrow I'll talk more about gas observations of protoplanetary disks. It's a pretty arbitrary and artificial distinction, like I said, because a lot of the phenomenology that I'm going to talk about today depends on the interaction between dust and gas, and so you need observations of both to understand particular phenomena. So I might actually revisit some topics tomorrow that I'll talk about today. But basically today I'm going to talk about protoplanetary disks for the most part, and I'm going to talk about dust for the most part. So the structure of the talk is also, I'll start off with a little bit of general background material, and then I'll get into, I've organized it by topic. I tried to pick a few big questions that I thought were either very fundamentally important or very timely, things that have recent interesting observations, and kind of go through those topics as a way of showing you sort of what the hot observations are and helping you kind of identify some directions for your modeling to go. So the other caveat at the beginning is that I have a serious bias towards radio observations. I am a radio astronomer by training, and so most of what I know is about radio astronomy. And I think that's okay, actually, because we are now living in the era of ALMA, and ALMA is very, very exciting for a lot of the modeling that you guys will be doing. So I hope you don't mind if my bias is towards radio astronomy, although I have tried to include some of the exciting observations from other wavelengths as well. Okay, so to start off, dust versus gas, and a little bit about sort of the evolutionary stages that I'll be talking about. Just general background for those of you who might not be familiar with the terminology that I'm going to use. When we look at protoplanetary disks, we basically see two main endpoints of evolution for these disks. They're the protoplanetary disks, what I'm going to call protoplanetary. It's a loaded term. It just means that these disks seem to have planet-forming potential. And these are the disks we find around young pre-main sequence stars. They're very, very gas-rich. About 99% of their mass is in gas. And the dust that we see in these disks appears to be more or less primordial. And by that I mean that it seems to be left over from the formation of the star. It might have undergone some growth. You might have large grains in the disk that didn't exist in the real primordial material from the cloud. But it's undergoing kind of reprocessing, but it's still first-generation dust. It's left over from the formation. And then on the other end of the spectrum, we have debris disks that you see around main sequence stars. A while ago, I would have said that these have no gas, but that's not necessarily true, as I'll talk about a little bit tomorrow. And so they have very, very little gas in them. And the dust that we see in debris disks must be second generation. If you calculate the lifetime of a dust grain in a debris disk, it's much shorter than the lifetime of the star. So the dust that we see in debris disks has to have been regenerated by some process, presumably grinding collisions of like Pluto-like objects in these disks. And then there's the transition between them. And these transitional disks that seem to be intermediate in some sense between protoplanetary and debris disks are really, really exciting. They're the topic of a lot of intensive study at the moment, so I will mention those in my talk today. But I will focus mostly on protoplanetary disks. So again, some of the salient facts that you should remember. About 99% of the mass is in gas. The opacity of protoplanetary disks is dominated by dust. However, the gas dominates the dynamics of protoplanetary disks. So today I'll be talking about the continuum emission from the dust, but keep in mind that the gas is really controlling where the dust goes to a large extent. And also, the gas-dust interactions depend on grain size, and that's something that I'll mention both today and tomorrow. Oh, I also wanted to say, this is, again, meant to be an interactive lecture, so if you have any questions, especially during the introductory material, please stop me. I can easily talk for an hour, but I would rather not. I'd rather hear your questions. Okay, any questions about that so far?
What do you mean by primordial dust?
What do I mean by primordial dust? I mean that the dust seems to have, essentially, it seems to be the dust that started off in, these stars and disks are forming from giant molecular clouds out in space. The molecular clouds collapse. It seems like it's dust left over from the collapse of the cloud. Like I said, we do see growth, and I'll talk about that more today. So we see larger grains than we see in giant molecular clouds, but we think that the dust is basically left over from the formation of the cloud, in contrast to the dust that we see in debris disks that had to have been incorporated into a larger body and then re-released later on. So that's the second generation compared to the primordial. Any other questions? No. Okay. So a little bit about circumstellar disk structure so that you can understand some of the tracers that I'm talking about today. On the left here, we have a spectral energy distribution of a star surrounded by a disk. So the star is just a black body, and then the disk emission comes at longer wavelengths than the peak emission of the star for the most part. So the star is sending out lots of light, the dust absorbs light from the star, it gets heated up as it absorbs that light, and then it re-radiates at longer wavelengths. And I'll just highlight the different sections of the disk spectral energy distribution and show you what they correspond to in my cartoonish diagram here of a star surrounded by a dusty disk. So first of all, at short wavelengths, we observe light from the optical and near infrared. And here I've highlighted the innermost parts of the disk. Now, of course, you can make scattered light images of the entire circumstellar disk. But when you look at the spectral energy distribution, what you're seeing is at these short wavelengths, the dust emission is dominated by the hottest dust, which comes from closest to the star. So at these very, very short wavelengths, most of the emission that you see in the spectral energy distribution comes from very close to the star, and it's very hot. So some of the challenges at optical and near-infrared wavelengths, there's a very strong contrast between the disk and the star. So as you can see, the star is about as bright as the disk at these wavelengths. But the problem is that the star is all in one point, whereas the disk emission is spread out. So the star is incredibly, incredibly bright compared to the dust emission, and it can be very hard to subtract. And so you see a lot of images of circumstellar disks at optical and near-infrared wavelengths, and the biggest challenge is removing the star from the image so that you can see the dust around it. The dust is also optically thick at these wavelengths, so you're only seeing the surface of the disk. And there are techniques that can get you very, very extremely high resolution at these wavelengths, which I'll talk about a little bit later on. Aperture masking interferometry is a very popular one at the moment. And like I said, the emission at these wavelengths is dominated by the inner roughly 1 astronomical unit when you're looking at the spectral energy distribution. As you move out to the mid-infrared, this section here, there are a few things that happen. First is that the contrast between the disk and the star gets better. It's easier to image the disk. The disk is still optically thick at these wavelengths, so you're still only seeing the surface, but you're seeing the surface that goes out a bit farther in the disk. It's dominated by approximately the inner, roughly 10 AU. Another interesting thing that happens at mid-infrared wavelengths is that you get these dust and gas spectral features. This here is a 10 micron silicate feature. This is like a spectral line of dust. And so this can tell you a lot about the mineralogy of some of these young systems. And then finally, when you get out to the longest wavelengths, you finally start to see through the disk. The disk becomes optically thin. The contrast between the disk and the star is essentially zero. When you look at radio images of circumstellar disks, you're basically not seeing the star at all, except in a few very unusual circumstances. Like I said, the dust becomes optically thin, so that's why the submillimeter and radio part of the spectrum is incredibly important for tracing the mass distribution in disks. Because at all of the other wavelengths, you are really just seeing the surface, so you are essentially tracing temperature as a function of distance from the star. But you have to get the disk optically thin before you can actually figure out where all of the mass is located and get down to the most interesting planet-forming region of the disk, where most of the planet-forming material is located. You also get, in this part of the spectrum, molecular lines, both optically thick and optically thin transitions. Oh, was there a question?
Yeah, when you say high contrast or strong contrast, you mean in this context that it's hard to tell them apart?
Yeah, so strong contrast means hard, and low contrast means easy.
Rather counterintuitive.
Oh, okay. So when I'm talking about the contrast, basically, this is sort of actually approaching the problem from an optical point of view, where when you look in the optical, the star is incredibly bright compared to the disk. And that becomes less and less true as you go to longer and longer wavelengths. That's the essential point to keep in mind. Okay? All right. So molecular lines in the millimeter, both optically thick and optically thin transitions. And this is incredibly important because it provides access to that gas component that is 99% of the mass and dominates the dynamics in the disk at these young stages. So millimeter is also very useful for studying that incredibly important gas component. And the problem, of course, as you go to longer wavelengths, is the spatial resolution. So with sort of, I don't even know how to describe it now. I used to say existing millimeter facilities, but ALMA exists now, so I can't say that anymore. With sort of last generation millimeter facilities, we were getting spatial resolutions of, at most, a fraction of an arc second, like a few tenths of an arc second. Already with ALMA, we're starting to surpass that. Cycle 1 will surpass that. And ultimately, we'll be talking about hundreds or even thousands of an arc second spatial resolution. So we're actually getting into a comparable spatial resolution to the optical regime. And actually, that's also true with the Very Large Array and has been true for a long time. The problem with the Very Large Array and circumstellar disk observations is that most of the disks haven't been bright enough to observe. But now that we have sensitivity increases with the EVLA, that's also becoming increasingly important. And I'll show you some EVLA data today. Any other questions before I move on? No. Yes?
Which component, which component do high-wave radiation, high infrared radiation trace?
What's that? So which
component on the disk?
The infrared radiation?
Far infrared radiation.
Far infrared radiation. Okay, so that's, yeah, I guess, so this turnover that happens here is sort of, I guess, what you might call the far infrared. And so it's still optically thick in the far infrared, so you still get the surface of the disk, but you do see sort of farther out in the disk. Like I tried to emphasize here, sort of at the shortest wavelengths, you're really mostly seeing emission from the inner parts of the disk, and as you go to longer and longer wavelengths, you see farther out in the disk. But you know, depending what you want to call the far infrared, if you're talking about sort of Herschel wavelengths maybe, you're still seeing optically thick disks in the surface of the disks, at least for the protoplanetary disk stage. Yes?
Just kind of considering more like post-class 0 where you have your envelope.
Yeah, post-class 0. I left out that slide. I usually show a slide where I have class 0 and envelopes and infall, and so this is after all of that, when everything is settled down, and you basically just have your pre-main sequence star surrounded by a disk. No more protostars. I'm ignoring all of that very exciting research that other people do. Yes. Any more questions before I move on? Okay. So the big questions about dust that I wanted to talk about today, and you know, we'll just see how far through I get. We don't have to talk about them. I've sort of put them in general order of importance and interest and recent data. So first of all, where is the mass and how much is there? This is an important question because if you want to understand planet formation, you need to know where the material that the planets are going to be made out of is located in the disk. How quickly do the grains grow? So not only do you want to know where the material is, but you want to know what state it's in. Is it all very small grains? Is it very large grains? What does the size distribution look like? And how does that change as a function of position in the disk? And how does it change with time also? When and why does the dust disappear? So we know that at some point protoplanetary disks dissipate. One of the very important questions recently has been, why does that process happen and when does it happen? And so not only are we finding new insight into what causes the transition from protoplanetary to debris disk, but we're also finding some unusual disks that seem to challenge the 10 million year deadline that has become canonical. What creates structure in the dust? I wasn't able to ask that question until recently, because until recently there wasn't actually very much evidence for structure in the dust of protoplanetary disks, but I'll show you some today. And what can dust tell us about planets? This at the end is the last thing this is the only part of the talk that really deals with something other than protoplanetary disks. This will deal with debris disks, so we'll see if we get to it. But this is something that I'm having a lot of fun with in my own research these days. Okay, so where is the mass? How much mass is there? So the how much mass is sort of the simpler part of the question to answer. So as I said earlier, you really, really need millimeter and radio measurements to ask this question about how much mass there is and where it's located, because the disk needs to be optically thin. You have to be able to see through the disk if you want to know where all the solids are located. So probably the best recent work about how much mass there is in circumstellar disks comes from Rita Mann's thesis. She graduated in 2010 or maybe 2009. Anyway, this is part of her thesis work where she actually worked mostly in Orion, but then compares the disk statistics of Orion to Taurus Auriga and Rho Ophiuchus, which Sean Andrews had surveyed for his thesis previously. So here they are. This is how much mass. So this is the x-axis down here is the mass of the disk. This is, so basically what happens here is that she's taking the millimeter fluxes, assuming a distance to the star. There's probably about a 10% uncertainty on most of the distances, so that's a slight source of uncertainty, but not the dominant one. You assume a temperature for the dust, which is essentially based on the size of the disk. It seems like actually a characteristic temperature of about 50 Kelvin works for most of these systems, but that is also another slight source of uncertainty. And then finally, you divide by the mass opacity, which is the really big source of uncertainty here. You have probably a factor of 4 wiggle room in the masses with the mass uncertainty out at these long wavelengths. And also, when you look at millimeter wavelengths, you're picking up sort of millimeter-sized dust particles, but you're completely missing emission from things that are sort of rock size or larger boulder size. You don't see any of the emission from basically boulder size objects. And so you can lock up an arbitrary amount of mass in boulder size objects. So you can think of these as sort of a guesstimate of disk mass, and also it's very much a lower limit because you have no idea how much material is locked up in larger objects. Okay, so all of that said, how do the disk masses vary with environment? So as you probably know, Taurus Auriga star forming region and the Rho Ophiuchus star forming region are low mass star forming regions. They're, well, Taurus is extremely dispersed. It's not very concentrated at all. Ophiuchus has a little bit more concentration. But compared to Orion, of course, there's a lot less high energy radiation in these regions. So this is in the center of the ONC, and you can see that the big difference between these, so here's the completeness limit, first of all. Don't pay attention to the low mass tail of the Orion mass distribution because it's just a completeness limit. Because Orion is so much farther away, it's hard to see the fainter disks. That's all that's happening there. But the thing that is very robust is the fact that in the center of the ONC, there are essentially no massive disks. And that effective environment has to do with the fact that there are extremely massive stars emitting a lot of extremely high energy radiation emission that's photoevaporating these disks very rapidly. So essentially, the most massive disks are just gone. There's nothing. Whereas in Taurus Auriga and Rho Ophiuchus, you do have this high mass tail of extremely massive disks. The low mass tail seems to be pretty common to all 3 regions. So you see a lot of low mass disks, but in Orion, there's basically, you just don't have enough, you can't maintain these extremely massive disks. So no massive disks in the center of the ONC. There are a few on the outskirts that have been found. And low mass star forming regions show a broad distribution of disk masses, including both high and low mass tails to the disk mass distribution. Yes?
Is the typical stellar mass in each of these regions?
Oh, that's a good question. Yeah, so these are all lumped together. So that's another question that you would like to answer, is there a correlation between the mass of the star and the mass of the disk? And so, of course, there are more massive stars in Orion and fewer massive stars in the Taurus and Ophiuchus regions. So, so you could try to account for that when looking at this, which they don't really do here. But it's an interesting question. Does the mass that you observe correlate with the mass of the star? And at least in these small, relatively small-scale surveys, the answer is not really, actually. So there is not really an observational correlation between the mass of the disk and the mass of the star that it orbits. Yeah.
And it's also, it's not like the stars in Orion are systematically more massive.
Right.
Like the typical star is exactly the same.
Yeah.
Maybe you got a ton of M stars.
Right. So I don't know how the sample is selected, but if
the sample is totally flux limited. So they just point millimeter telescopes up and they say, where do we see a disk? And then they count it. So it's just a flux limited survey of disks.
But they're surveying every star within their field of view, right?
Right.
Right. So it's effectively number weighted, which means that it's probing the exact same massive star as the other samples. Basically.
That's true.
They're just there are more massive stars present, but by number they're negligible.
Yep. Yes.
How strong is the result? Because you suppose that some chemical composition for the opacity and the temperature maybe depends on the opacity and the flux.
Well, that's why I gave that caveat. This is just totally. This is really just the simplest possible way of converting millimeter fluxes into a disk mass. This is all that's happening under the hood of these kinds of surveys.
Depends on everything.
Everything depends on everything. It's true.
There is convergence. You suppose on chemical composition, and then you assume a temperature, and then I don't know.
Yeah. So generally, the opacity that's assumed assumes sort of an astrosilicate composition, which seems to work for most of the disks that we know about in nearby young star-forming regions. But yeah, you're right. We don't actually know. That's why I say to be very skeptical of these disk masses that are calculated based on millimeter fluxes. The other reason to be skeptical is because right here we're only counting 1% of the mass of the disk, right? This is only the mass in solids. We've totally ignored the gas so far that is 99% of the mass of these young disks. So I'll come back to that later on, actually tomorrow. Any other questions about this? No. Okay. Okay, so the next question is, where is the mass? So the historical classical way of thinking about where is the mass in a planet-forming disk is to look at our own solar system before we knew much about the disks and planets around other stars. So this, of course, is the minimum mass solar nebula. I assume everyone here is comfortable with the concept of the minimum mass solar nebula? Yes, no? No, okay, I see a few shaking heads. All right, so the idea here, I'm happy to describe it. The idea is, so this is Mercury, Venus, Earth, Mars, asteroids, Jupiter, Saturn, Uranus, Neptune. And what they've done here is they've taken all of the bodies in the solar system, they, in their minds, ground them all up into little dust particles, spread them out until they were halfway between the orbits. So you can see that's why the bars reach from one orbit to the next. And then they bumped up the composition. So like the Earth has very little hydrogen and helium in it. So they bump up the composition and say, okay, how much mass in gas, assuming solar composition, would you need to get this much solids? And then they say, okay, well, what does that mean for the surface density of the solar nebula as a function of radius? So this is the minimum amount of mass you would need in solar composition material to get the solids that we see in our own solar system now, to get Mercury, Venus, Earth, et cetera, et cetera, et cetera. So from this, people tend to say, okay, we're going to call this the minimum mass solar nebula. And therefore, looking at this plot, clearly the surface density falls off as r to the minus 2, right? Right? Do you see it? Yeah, maybe, maybe not. So r to the minus 2 kind of goes like, what is it? So this is 2 orders of magnitude on this plot, and here's 1 order of magnitude, so it would kind of go like this. So that's the minimum mass solar nebula. This is where it comes from, seriously. Everybody uses this in their models, and it comes from this really ugly plot here, where even you can see here, he's just sort of drawn a line here saying, this doesn't look so good, so I'm just going to ignore it. So that's the minimum mass solar nebula. You can tell that I'm very skeptical of the minimum mass solar nebula, and I'll show you why in a minute. This is the minimum mass extrasolar nebula from around 2004 that Mark Kushner did exactly the same thing with a bunch of extrasolar systems. I don't actually know if he specifically selected against hot Jupiters, which of course, including a hot Jupiter, which we think migrated to its current position from much farther out in the disk, would really bias your minimum mass solar nebula. But this minimum mass extrasolar nebula actually looks pretty much like the minimum mass solar nebula. So that's not so bad, where we're only looking at Jupiter, Saturn, Uranus, and Neptune and ignoring the rest of the disk. So we can do better today because we can actually go out and observe these solar nebulas, these circumstellar disks. So here is a sample of objects. So this is Sean Andrews' paper from 2009, and then there are a few more from 2010. And so these are resolved, spatially resolved millimeter observations of the dust in these disks. And so using one of the codes that you will play with next week, RADMC, what Sean did is he took all of these resolved observations and the spectral energy distributions and tried to fit them both simultaneously to derive the disk structure. And this is what you get. So first of all, what do all of these parameters mean? Well, I'll explain these three. These two basically have to do with the vertical structure of the disk, and they're constrained by the spectral energy distribution. They're basically how puffy is the disk and how does that puffiness change with radius. But these three are, first of all, the mass of the disk. So how much, if you look at surface density as a function of radius, how much mass is just integrated under the curve. And gamma is that slope with which it falls off with radius, which was 2 for the minimum mass solar nebula. And RC is a characteristic radius. It's not actually where the tail starts to turn over, but it's related to that. It's sort of, you can think of it as this, the functional form that he was using was effectively a power law with an exponential tail, and this is sort of the scale length of the exponential tail. So this is what it looks like, and hey theorists, the minimum mass solar nebula has gamma equals 2, but the real disks we observe here have gamma equals 1. You can see there are 0 disks out at gamma equals 2. So when we go out and look at a protoplanetary disk, at the dust in a protoplanetary disk, we see that the surface density appears to fall off with radius as r to the minus 1. Now, there are reasons to be skeptical of that too. Not only this idea about the opacities and the composition of the dust grains, which actually doesn't affect the slope as a function of radius, but because the grains might change their size distribution as a function of radius, which is an idea that I'll come back to in a minute. So there is this sort of disconnect between the disks that we observe and the minimum mass solar nebula that theorists tend to use in simulations. But there might be reasons for that, so maybe it's not so bad. But I do want people to be aware of it because theorists still love the minimum mass solar nebula, and I'm not sure why. OK, so a few things to note about this. Using standard assumptions, most disks have roughly as much material as the minimum mass solar nebula. So here is the minimum mass solar nebula for, I think, Saturn, Uranus, and Neptune. So out at the right radii, I think that's right. And you can see that most of the surface density distributions that we derive using these standard assumptions for the opacity of the dust grains actually go through the points in the minimum mass solar nebula. So that's good. It seems like most disks have enough stuff to form our solar system. Even if that requires 100% efficiency, at least the stuff is there, right? It's not so bad. Another thing that came out of this study that I don't hear people talking about a lot, but I think it's interesting, is that on average, brighter disks seem to be larger. So this is a horrific plot of deprojected baseline. Basically, this means small scale stuff, and this means large scale stuff. This is like the distance between your closest antennas and your most distant antennas in an interferometric array. So think of it as like it's the Fourier transform of the brightness as a function of radius. So, so it's just an inverse relationship. Things that look wide on here are actually narrow, and things that look narrow on here are actually wide. So the bright disks are bigger than the faint disks on average. And that's sort of a surprising result that I don't think we really understand yet. Yeah? No, not necessarily. Good job thinking about things as a Fourier transform, but no. If they had more small scale structure, so if they had more small scale structure, you would see more power out here at the long baselines. You would see this might go up, and we don't see that. But yes, good Fourier thinking. OK. So actually, that was the end of my where is the mass and how much question. So are there any questions or thoughts about that before I move on?
So the profile does not depend on the stars, the kind of stars you observe?
So this was averaged over stars because, as you could see, the numbers in the sample, they're only like, a dozen disks in the sample. So this paper didn't separate out stars of different types. So they're all kind of averaged together. Yeah. Any other questions? No. OK. So question number 2. How quickly do the grains grow? And so essentially the holy grail here is we would like to know the size distribution of dust grains in a disk as a function of position. So as a function of radius, but also as a function of height above the midplane. OK. So to first order, we learn about grain growth by looking at the long wavelength SED slope. Why does that work? Well, OK. This is the number of grains of a particular size, and we tend to assume that that is proportional to the size of the grains to some power. So we assume that the grains have a power law size distribution. And there are all kinds of theoretical reasons to assume that, but that's what we tend to assume. OK, so we want to know Q, which is the power law of the grain size distribution. So that tells us sort of how the mass is allocated between large and small grains. If Q is very steep, it means that there's a lot of mass in the small grains. And if Q is very shallow, it means that more of the mass is in the large grains. I've already shown you essentially this equation just rearranged now. What we measure is flux, but the flux is proportional to all of this other stuff. The total mass of the dust grains, the Planck function for the temperature of the dust grains, and the opacity divided by the distance squared. So this is what we observe. We tend to assume that kappa is a power law as a function of frequency with power law index beta, works for the ISM, seems to work in circumstellar disks. And relating, so this is the really important equation here. This relates beta, which is the power law opacity, to Q, which is the size distribution. So we can look at the disk, and we can look at the spectrum of the disk, the spectral slope of the disk, and we can try to pull out beta from the spectral slope of the disk, right? Because how does this depend on frequency? Well, the Planck function is here, but we know how the Planck function works, right? If we can take a good guess at the temperature of the grains, we're pretty solid on the Planck function. But the other way that the flux depends on frequency is kappa here. So if we can get a pretty good handle on the temperature, which we think we can, then by looking at the slope of the spectrum, we're actually looking at the slope of the opacity law. So that's what goes on here. And then we can take the slope of the opacity law and relate it to the slope of the grain size distribution. OK. Oh, and beta S is just for the smallest grains. And that has some value that Bruce Drain has calculated. So we trust him. OK. So here's an example for Fomalhaut, where you can see this is the flux as a function of wavelength. And here it goes. In the long wavelength part of the spectrum, it goes down. Nu is 2.7. So you plug that in here. 2.7 minus 3, so it's negative over 1.8. So then you get some answer out for, sorry, you get, wait a minute, no, beta, sorry. So first of all, you have to take out the Planck function. It's 2, so you're left with 0.7 for beta. 0.7 times 2, 1.4 equals Q minus 3. So that actually doesn't work. I should never try to do math on the fly. Oh, because this should be negative. OK. Anyway, you can see basically, so you measure this slope, you plug it in here, you get the Planck function, and then whatever's left is beta. So that's where this comes from. OK. But that's only so interesting, right? This is averaged over the whole disk. Part of the problem here is that things might change as a function of position in the disk. So what you really want to do is radially resolve the disks and then look as a function of radius at how the long wavelength slope of the dust changes. OK, so it sounds very simple, right? You're like, well, that's obvious. But the problem is that until recently, we didn't have nearly enough sensitivity to be able to do this. So this is really new stuff, like hot off the presses in the last year or two. So radially resolving kappa. So here's an example. This is from Laura Perez's thesis at Caltech. And here she's resolved a disk with the submillimeter array at 0.8 microns all the way out to the VLA at 9.8 microns. So an order of magnitude in frequency. OK, so once again, one of these horrific UV distance plots. So once again, you can see that the long wavelength disks are larger, smaller. So they're closer to unresolved. So if this were a point source, everything would be 1. However, it's not. But the closer it is to a constant, the closer it is to a point source. So the thing that's stretchier is actually smaller. So the disk is smallest at the longest wavelengths and largest at the shortest wavelengths, right? So as you step out in radius, the disk gets more and more compact. And that means that the large grains are more and more concentrated towards the center of the disk. So you can use that to derive beta as a function of disk radius, and that's what Laura's done here. And you can see that it looks like beta increases as a function of radius, which means more of the smaller grains are concentrated in the center of the disk. Sound good? Any questions about that? No. OK. Now you can take this even farther, and you can say, OK, well, that was great for a face-on disk. What if I now look at an edge-on disk? So there are disks that you can view edge-on, where you can actually spatially resolve the vertical dimension of the disk very easily. So one of these examples is the butterfly star. Here it is at a range of different optical and infrared wavelengths. And this is a sort of combined picture of these 3 different wavelengths. And here it is at millimeter wavelengths. So if you imagine drawing the contours on top of the dark lane here, you can see the scattered light reveals more of the disk atmosphere, and the long wavelength stuff actually shows you where the mass is located all in that dense midplane. So by analyzing these, by combining the images going across the spectrum with a spectral energy distribution, they were able to find evidence for grain growth to up at least 100 microns, which is sort of obvious if you're seeing millimeter wavelength emission, but also vertical settling, so they could actually see that the size distribution changes as a function of height above the midplane, which is an important step in planet formation, getting the large grains to sort of congregate towards the midplane. And then also at the same time seeing radial segregation of the grains, where the disk is actually smaller in 1.3 millimeter emission than in the scattered light emission. Was that a question up there? No, just a hand raise, okay. So yeah, so now within the last couple of years, it's become possible to actually look at how the size distribution of grains changes, not only as a function of radius in the disk, but as a function of height above the midplane. And that's something that's very new and very exciting in understanding planet formation potential in these disks. And I'll come back later on, actually tomorrow, I think, and I'll discuss more about why the disks look the way they do, like in that in Laura's thesis work that I showed you. Because when you actually look at the images of the disk, you can see that the very long wavelength images actually look physically more compact than the shorter wavelength images. And part of that is due to grain growth, but part of it is actually due to fragmentation and radial drift, which is a gas-dust interaction process that happens, and that's very dependent on grain size. So I'll come back and talk about that more tomorrow. OK, on to question 3. When and why does the dust disappear? So, OK, how am I doing on time? Good. So the first question is, when does the dust disappear? And the way that we figure out when the dust disappears, this is sort of a large sample of disks. This is sort of a statistical answer. So here, as a function of age, we have a bunch of different clusters. So I don't know, you can probably find your favorite cluster on here, although they're not labeled. So Taurus is down at a couple million years, and SCO-Cen is a little bit older, and whatever. So these are just a bunch of different clusters of disks. And within those clusters of disks, you count how many of them have disks. And you can see that the fraction is extremely high at very young ages. Nearly all stars start off with disks. And then as you get out to an age of about 10 million years, essentially none of the stars have disks beyond that point. Yes?
I was going to mention what I learned 2 weeks ago at Protoplanetary Planet 6 is that the x-axis here is being recalibrated.
Yes. I was going to mention that, okay, and another thing. No, but thank you. No, you can talk. Do you want to say it?
No,
go for it.
If you're going to say it anyway, say it.
No, you go for it. I'm talking too much. I need a break.
Okay. Well, just that all of these ages are based on pre-main sequence evolutionary tracks, which differ systematically, it seems, from the main sequence evolutionary tracks due to subtle technical issues. And it seems that the pre-main sequence tracks were probably the ones that were systematically off, and so all of these ages got older.
Yes.
So basically, take the numbers on those x-axes and multiply by something like
2-ish. Yeah. Yeah. So so actually it's increased by about a factor of 2. So this is now about 20 million years, which is good from a planet forming perspective, right? Because as you guys all run your simulations, you'll find, well, and as theorists for many years have been finding, it's really hard to form Jupiter and Uranus and Neptune by 10 million years, which is around the time that we think these disks dissipate. So that actually really helps in terms of connecting our understanding of the fact that now we think there's at least one planet per star in the universe, right? And the fact that we were seeing these ages that were just kind of on the uncomfortably short edge of how long we actually think it takes to form planets. So there's that issue with this plot. This is from 2009, of course. And the other issue with this plot is the y-axis. So we've already talked about the x-axis. Now let's talk about the y-axis. How do you count disks? Well, we'd love it if we could get really deep millimeter observations of all of these things so we'd know how much mass there was. But the problem is that's just not feasible. It takes a lot of time. It's very telescope intensive. So what this is probably, I actually don't remember how Eric calculated this, but most of the time it's like near to mid-infrared excess. So you take the number of stars, so you basically look and see, does it have an infrared excess, yes or no? And if the answer is yes, then you count it as a disk-bearing star. But the problem is that as disks evolve, we know, as we've already seen a little bit, and as I'll show you more later on, we know that there are disks that clear out their centers of dust and then persist for much longer, that are just as massive as the real primordial protoplanetary disks. So this doesn't count transition disks or any kind of disk with a central clearing, and we know that those disks can still be very massive and still have quite a lot of planet-forming potential. So you also have to be careful when you look at the y-axis, because probably we're missing a lot of still very massive disks. Okay. So the next question is, why did the disks disappear? And to answer the question of why the disks disappear, you need a little bit more information than just what's the fraction of disks as a function of age. So dissipation timescales and resolved imaging. So here are a bunch of images of what I've been calling transition disks. And these are disks that are just like protoplanetary disks. They're found in the same clusters. They're neighborly with these protoplanetary disks. But these are ones that have giant holes in the center of their disks. So what are some of the relevant facts about transition disks? First of all, they look like protoplanetary disks with their middles cut out. So I did show this, I didn't talk about it, but if you look at the surface density distribution that you derive for protoplanetary disks and transition disks, they're basically the same. So you have surface density as a function of radius, and you see it falls off just the same, except with the transition disks, it's like someone took a chunk out of the middle and then kept going. So they're still very massive, but there's just no mass in the middle. Some of them have centers that are depleted of small grains, and others don't. So here's an example of, this is a spectral energy distribution where you can see, if you think of wavelength as a proxy for temperature, where hot stuff is over here and cold stuff is over here, then you can also think of it as a proxy for radius, where stuff close to the star is over here and stuff far from the star is over here. So when you chop out a bunch of the short wavelength emission, it's an indication that you've chopped out material from the center of the star. So that's how people first identified transition disks. And you can see, right, stuff chopped out from the middle looks like stuff chopped out from the middle when you go and take a picture of the disk. Very neat. Except not all of the disks look that way. So this disk, for example, has what you would look at this and you would think it was an intact protoplanetary disk. So that tells you one of two things, right? Really what's happening here is that the small grains are not depleted enough to register on the spectral energy distribution. So either the hole is too small to show up on the spectral energy distribution, which isn't the case here because we took an image of it, which means it's pretty big. We can only image big holes at this point. So what's really happening here is that probably small grains have leaked into the hole. So there's a deficit of large grains in the middle, but small grains seem to be filling up the hole. And I'll come back and show you some images later on from the SEED survey that actually show pictures where you can see a hole in the millimeter emission, but there's no hole in scattered light. So all of these processes are dust size dependent as well. Also, don't believe the size estimates based on SEDs alone. If that wasn't enough evidence for you, this one here, looking at the spectral energy distribution, it was predicted that the central cavity was 4 AU in radius, and when we went and imaged it, it was 32 AU in radius, so off by almost an order of magnitude. So the SED-based estimates are not good. Although, of course, they're the best we have for most of these systems, because SEDs are much easier to construct than images. Also, when you look at all of the different pieces of evidence, the sizes of the holes, the mass accretion rate onto the holes, at least for these extremely large disks that still have relatively high mass accretion rates, there are people who would argue, mostly people who study photoevaporation, but it seems like all of the lines of evidence point to these are probably not photoevaporation. Probably there's something else going on here. And I'll focus on this disk for the next couple of slides and show you some of those pieces of evidence, not all of them. Yes? Good question. No, not as far as we can tell. Of course, it's very hard to age date individual stars within a cluster, but we find these stars sort of throughout the cluster, and there's no indication that the transition disks are systematically older. One of the only sort of demographic differences that we seem to see is that maybe there's an indication, and people have argued about this over the years, but there seems to be some indication that the mass accretion rates are lower on average in transition disks by maybe a factor of 3, maybe an order of magnitude. But they're not 0. They're still measurable. They're just a little bit lower than the protoplanetary disks, and I'll talk about why that might be.
And these are mass accretion rates coming from H-alpha?
Mostly H-alpha, yeah. There's some continuum veiling measurements. Most of them are H-alpha or some other equivalent with proxy that stands in for H-alpha. Yes?
Is it true that they have some axisymmetric?
That they have?
Axisymmetric features?
Yeah, yes, I'm going to talk about that later on. So some of the axisymmetric features that have been reported are not real, but recently, like within the last year or so, there are some that are very believable. So yes, there are some of these disks that do have non-axisymmetric features. Yeah, but I'll come back to that in a little while. Yes?
Could you guide my eye? What am I supposed to interpret as a whole? Like
Yeah.
the bottom two images?
Yeah, see these blobs? Okay, so what's going on there? So these two disks are actually, you also have to think of the geometry of the disk. So, right, if this were a face-on disk like this one, well, actually this is sort of inclined too, but this hole happens to be bigger. So you can see that there's a hole in that disk, right? But you can also see that the two edges are a little bit brighter, right? And the reason for that is because if you incline the disk a little bit to the line of sight, it's essentially like a limb-brightened ring. So the center of the disk is the hottest and most dense, and so you incline that, and then the stuff along the edges piles up along your line of sight, and it looks brighter. And so what you're seeing here is a limb-brightened ring where you just haven't really resolved the actual hole in the center. And the more inclined it is, the more it'll look like 2 points instead of a ring. So this one looks kind of like a ring. Most of these just look like 2 blobs. That one looks kind of like a ring. That one looks kind of like a ring. But the 2 blobs are just the limb-brightened inner edge of the dust disk. Yes? Good question. Well, you don't from this image. You really need statistics to tell the dissipation timescales, so that's why you need things like this. This is how we tell when the dust disks disappear. And this is the resolved imaging is that's the way we tell why the dust disks are disappearing. Yeah. Any other questions before I move on? Okay, so I'm going to show you now a little bit more about Lick calcium-15, which has been a really interesting case study in the study of circumstellar disks. So Lick calcium-15 has also been resolved at scattered light wavelengths. So this is one of the first and most spectacular results from the SEED survey, which is a survey with the Subaru telescope, led by Motohide Tamura. And so this was the picture that Catherine Espaillat and others had built up over the years of what a transition disk probably looked like. So we've got some disk out here with this wall at the inner edge of the disk where light from the star is essentially coming out unhindered and hitting the inner edge of that wall and heating it and puffing it up, so you get this almost vertical wall at the inner edge of the disk. Maybe there was a little bit of material inside, maybe a little bit of junk kind of in between here. And that was really borne out quite spectacularly in this first imaging result from the SEED survey. So that's really nice. The other thing that's interesting about this is that the center of the ring, which you can see the center of these 2 sort of ellipses are marked with the 2 crosses here, is offset from the star position, which is marked by this white cross over here. And so that seems to be an indication of eccentricity. And of course, in these very gas-rich disks, it's extremely difficult to maintain eccentricity over a long period of time without a point mass of a young protoplanet or a stellar companion to do that for you. I should also mention that nearly all of these transition disk stars have been surveyed for stellar multiplicity at this point, and the stellar multiplicity fraction is extremely low. So that's one possibility for what could be clearing out the inner disk as a binary stellar companion, but we don't see them, so they really aren't there. So it has to be a lower mass companion like a planet. So this is another one of Sean Andrews' papers where here he's got very high signal-to-noise, long baseline observations of the Lick calcium-15 disk, and he tries out a bunch of different models. So he tries out one where it's sort of a gradual taper on the inside and outside, and that doesn't work very well. It doesn't reproduce the data. These are the best fits for all of these different types of models. There's another one where it comes in and basically gets chopped off, and that doesn't fit the data very well either. So there has to be some material in the inner disk. Whether it is that the disk comes in, gets chopped off a little bit, and then there's just a little blob of material in the center, that's a possibility. That fits reasonably well. Or the other thing that fits really well is this very interesting red line here. And this red line is sort of an analytical solution to the question of what happens if you plop a protoplanet in the disk and let the disk evolve. So this is actually what you would expect a disk that's cleared out by a planet to look like. And you can see that that also fits the data quite well. And then really the smoking gun in the case of lit calcium-15, so some large grains must be in the cavity, and the best fits the millimeter data matches the predictions for a planet carving out a gap in the disk. So here's the smoking gun for lit calcium-15. This is an image made with aperture masking interferometry by Adam Krauss and his collaborators. Here's the millimeter image. Here, if you zoom in on the center, there's actually some kind of point mass inside the hole in the center of the disk. Looking at this, you can see it's not quite a point, right? The red and the blue are two different near-infrared bands. I forget, one is, I think, H and one is L, I believe. And in one of them, it looks point-like. In the other one, there seems to be sort of a tail or something. And so it's not really clear exactly what this is, if it's the protoplanet itself or some kind of like spiral arm from the protoplanet or something like that. But there does seem, there's definitely a point-like object inside the inner cavity that's consistent with a protoplanet clearing out the gap. So there's another one of these disks as well. Here's T-Cha. That has some kind of point-like detection inside using aperture masking interferometry. So I'll come back tomorrow and talk more about how observations of gas are helping us to disambiguate the origin, the reason why these disks have these giant cleared out inner cavities. But just from the dust imaging alone, from the continuum imaging alone, you can see that there's mounting evidence that planets are probably clearing out the inner parts of the disk. Any questions before I move on? No? Okay. A few more results from seeds I just wanted to show you. So this is one of the seeds results where here the contours are the millimeter emission, and then the colors are the polarized scattered light emission. And so you can see that here's a nice example of a system where you see the hole in millimeter light, and then it very nicely traces a rim in scattered light. And the interesting thing that the authors point out here is that the scattered light is not axisymmetric. There's this depression on one side. Now, of course, polarized scattered light is a little bit complicated because you have this, all of these different scattering angles that might not be symmetric. So you have to be careful when you're looking along the minor versus major axis of the disk. But they do some of that analysis, and it seems like maybe there's actually something to this depression in scattered light that could be related to the presence of a planet in the disk. But of course, not conclusive. And here's another one. This is interesting because this is sort of showing us that the discovery of gaps in these disks is coming into its own with imaging now. So I showed you a bunch of images of transition disks, but those had all been discovered using the spectral energy distribution for the most part, although actually not all of them. In the millimeter survey that I showed you, it was basically a survey of the brightest disks in Ophiuchus, and about a third of them turned out to be transition disks just by surprise. And now we're seeing something similar in scattered light. When you just image a bunch of these disks in scattered light, a bunch of them turn out to have large gaps, even if the spectral energy distribution didn't indicate that they should have large gaps. So imaging is becoming just as important as spectral energy distributions now in identifying these transition disks. And it's far more important for measuring the size of the cavities because, as I showed you before, the size that you measure from the spectral energy distribution doesn't always correspond to the size that you measure with direct imaging. So this was a nice result from seeds. And then I'll show you this one briefly, but I'll talk about it more in a minute. Here you can see these gorgeous spiral arms in the disk. But the point here is that actually in the millimeter image, there's a gap. And the gap is like way out here. But you can see that there's a ton of scattered light material filling in the gap. So the question is, why would you see a hole in large grains, but a continuous disk in small grains? And I'll talk about that more tomorrow. OK, so before I move on to the next question, anyone have any more thoughts, concerns about transition disks? Yes?
So what's the fraction of the disks
that are transition disks? Yeah, good question. So if you look at spectral energy distributions alone, the estimate is around 10%. So that's what you'll see in sort of the large surveys. And the advantage of looking at spectral energy distributions is that you can survey a lot more stars. But then when you go to imaging surveys and you just look at these disks, like I said, in this survey of the brightest disks in Ophiuchus, about a third of them seem to be transitional disks, even though not all of their spectral energy distributions indicated that they should be. So it seems like the spectral energy distribution numbers of about 10% transition disks are probably a lower limit, and that as we do more imaging, we'll find that more and more of these disks are transition disks. The other thing to say about that is that right now, we can only image the largest cavities in these transition disks. So things that are tens of AU in radius. There are probably cavities that are even smaller that we have no way of knowing about right now. So I think probably the best estimate from imaging surveys right now is sort of 20 to 40%, and then we think that that's a lower limit because it only describes large cavities, and that there are probably more disks with smaller cavities. Good question, though. Anything else? Okay. So let's talk about this disk a little bit more. Now we'll get into the question of what creates structure in the dust. And like I said, this is a question that we couldn't even ask a few years ago because there weren't a lot of observations of non-axisymmetric structure in these disks. And this is really just happening over the last year or so. So here is a gorgeous image of spiral arms in the disk. You can clearly see two spiral arms extending inside the gap that's observed at millimeter wavelengths. The cause at this point is still fairly inconclusive. It could be planets, but it could also be, you can see that this star is a B, which means it has a stellar companion nearby. So it's plausible that the spiral arms could be generated by interactions between the neighboring star and the disk as they fly by each other in their orbits. One way to learn more about that is that we will be able to watch the evolution of this system, and we should see the spirals move over the next 10 to 20 years. And as we watch the spirals move and learn more about the mutual orbits of the two stars in this system, we should be able to disambiguate between the two origins. So that's a really beautiful result from the SEED survey. Here is another, so this is another ALMA result that, that came out this year that kind of got a lot of press. And it got a lot of press not for the reason that I'm about to tell you about, but for the reason that I'll save until tomorrow to tell you about, which has to do with the gas. So there are two really interesting things going on in this system. The first is that, well, so the thing that I'll tell you about tomorrow has to do with the gas. And you can actually see the gap in the gas. But not only can you see that there's a gap in the gas, you can actually see that there appear to be streamers crossing the gap falling onto the star. Which makes sense, right? Because I already told you that these disks are still accreting when they have large gaps. So we know that there must be gas crossing the gap, but we didn't know sort of the geometry of it until recently. And of course, only for this one system. Many systems could be different. So, but what does the dust look like? So here you can see the millimeter, the contours once again are the millimeter dust emission. And it seems to be concentrated on one side. And in fact, it is concentrated on one side of the star. So there's more dust on this side of the star than on this side of the star. The sort of orangey pixelated image that you can see down here is the scattered light emission from the star. So you can see there's a lot of structure. There's clearly something happening in this disk. But there's not much evidence of the extreme asymmetry that you see in the millimeter light, where this side of the star has about, as far as we can guess, about 10 to maybe even 20 times as much material as the other side of the star. So that's incredibly hard to do. And the contrast that's measured is really too extreme for eccentricity alone. So you could imagine that one of the things that could be going on here is if the disk is eccentric, well, you would expect some amount of pericenter glow, which means you would expect the flux to be higher on the side of the disk that's closest to the star, because that's the hottest material. So if you have a very eccentric disk, one side is going to be closer to the star, and so it'll glow because it's hotter. That can be balanced to some extent by the fact that in an eccentric disk, of course, the material will spend more time farther away from the star where the orbital velocities are slower. So you actually have more surface density far from the star, but you have more hot material closer to the star. So that actually tends to balance out the contrast that you see because of eccentricity alone. So the contrast that we see here is just too extreme to be explained with eccentricity.
Meredith?
Yes.
Is the thermal equilibration time really that short compared to the orbital time?
Yeah, because this is out at like 60 AU, right?
Okay.
So the orbital times here are, I don't know, what's the orbital time at 60 AU? Hundreds of years, right?
Okay.
And so the time for the dust to adjust its temperature is much shorter than that. Yeah. Right, so there must be something else going on here other than eccentricity. So what could possibly be concentrating the dust on one side of the star? So this is actually a physical concentration of the dust, not temperature differentials. And the answer that people like to float around is this idea of vortices, or dust traps in disks. And I'll show you a couple more examples that seem to be supporting this idea. Maybe. Of course, you guys are the theorists. I want you guys to tell me why this is happening. I'm just showing you cool stuff, and then it's your job to explain it, right? Here's another example, Lick-H alpha 330. Star in the middle, a little bit more stuff on one side of the star than the other. This might look like some of the other images that I showed you of transition disks. So why didn't I tell you that those were asymmetric? The reason why I didn't tell you that those were asymmetric is because when you actually make a model of an axisymmetric dust disk and subtract it off, you get no residuals. But here, that's not the case anymore, where they've actually made a best fit axisymmetric model of the disk and subtracted it off, and they still have very significant residuals. I think these are 246 sigma contours. So this is the new thing, right? People have been claiming clumpy structure in these disks for years, but the problem was it was never statistically significant before, and now for the first time it is statistically significant. So there's some asymmetry in the millimeter grains, and various simulations show that companions might be able to help trap the dust. So if you believe that these transition disks are cleared out by planetary mass companions, that is one way of trapping the dust, but it's not the only way. In this paper, they talk about a bunch of different methods, and they do point out in this paper, though, that Rossby wave and baroclinic instabilities are unlikely to be able to concentrate the dust this far from the star. And that's something that I don't know much about, but maybe Mark can comment on that at some point, I don't know. Or Jim, for that matter. Okay. Yeah. And then finally, this one has gotten a lot of press. This is another neat ALMA result, where in the micron, you can see, at micron wavelengths, you can see the dust is more or less continuous, and there are these two peaks on either side of the star that indicate that there's a central clearing. The CO is basically unremarkable. It seems to fill in the whole disk. But when you look at the ALMA image, which is in green on here, but looking at the significance over here, I mean, talk about a significant result, right? This peak is greater than 100 sigma. It's like 200 sigma over here, and there is nothing over here, right? So that tells you, I mean, this is really the nail in the coffin for me. It's like, is there any way you could possibly create a 200 sigma peak with nothing on the other side and not have a physical difference in the amount of dust on two sides of the star? And I think the answer to that is no. So it's far more pronounced and significant than any other source that's been observed so far. So I don't have a nice theoretical explanation for you because there really isn't one yet. People have been talking a lot about these vortices and these various hydrodynamic instabilities, but I think that these results are so new that people haven't yet had a chance to kind of match up the simulations in terms of their the intensity of the contrast that you can achieve and the spatial properties. So would it stretch out in this kind of banana shape like you see here? Is the length and the contrast that you observe in the images consistent with what you see in the simulations? And there haven't been a lot of good papers that have really tried to compare in detail the simulations with the observations yet. So I think that's kind of an opportunity at this point to try to understand these non-axisymmetric features in these disks. Any questions or thoughts about non-axisymmetry? Yeah?
With the symmetry structure, how much is tumor value?
How much is, oh, the tumor Q values? That's a good question that I don't know the answer to off the top of my head. Again, that would depend on the gas. Yeah.
Well, but if the mass is down to like 1/100th the solar mass, it's going to be Q's 100.
Well, yeah, so if you look at the mass ratio between the star and the disk, yeah, it's probably about 1%.
Right, but
Right.
I mean, yeah, Q is going to be, it depends on the surface density, but
Right.
for any, I think. I mean, maybe in the dust, the tumor IQ could be small.
Yeah.
The velocities version can be
Yeah.
tiny. But for the gas, it's going to be.
Right, right. So, and that's the other thing I was going to say, is that the other thing to remember is that in this disk and some of the other disks, there seems to be basically uninterrupted CO emission. It looks perfectly Keplerian and totally axisymmetric, which is of course difficult to say because most of the CO emission that we observe is optically thick. So if there were slight density contrasts, you might not see them because you can hide them in an optically thick disk. But people are starting to look at these disks with different isotopologues that trace closer to the midplane and that would trace the density contrasts more. And it seems like the density contrast in the gas is far, far less than the density contrast in the dust. So in addition to this issue of tumor Q, the gas seems to be relatively unaffected by whatever's causing the dust to clump up in this way. It's probably gas dynamics that are causing the dust to clump up in this way, but we just don't have a good physical description yet. Any other questions before I move on? How much time do I have? Oh, I'm out of time. Look at that. OK, so I'm going to skip the debris disk section of my talk, which was really not about protoplanetary disks anyway, so that's fine. So I guess for the end, I will just put up my last slide, and which has all the questions on it. And if you have any more questions about this, you can feel free to ask me. Thank you very much.